Hi everyone. So within our series on factor analysis, I think this is the fourth part, and today we're going to interpret two key outputs, which is the total variance explained and the Scree plot. Okay, so the data set and for other output interpretations, I request you to watch my earlier video lectures. Thank you. So talking about the total variance explained. So this is the table which is going to answer that, okay, these are the factors which we have extracted. These are the number of factors which we have extracted basically. So this allows us to decide how many factors or components to retain. So initially for our n variables, so we started with 16 variables, for example. Each of the variables is like a factor for us. So it's like initially we're going to start with each of the factors, each of the variables as the factors. Okay. So initially the factor analysis is going to extract all these n variables, and each factor has a quality score called an eigenvalue. So you look at this eigenvalue. So this is the quality score. So why is it a quality score? So basically eigenvalues are the variances of these factors. That is how much variance can be explained by a particular factor in the data. Okay, so only those components which have a high eigenvalue are likely to represent a real underlying factor. So the rule of thumb is we select all those factors whose eigenvalue is at least 1. So you look at this here. So you look at here. So wherever you see that the eigenvalue is greater than 1, we are going to take all those variables and those will become our extracted factors. We see that 2.4, 2.3, 1.9 and 1.57 eigenvalues are all greater than 1. So they're going to come here in the extracted sum of square loadings, which indicates that, okay, these are the factors which we have extracted. That is the 4 factors being extracted. So how does this calculation really come up? So I'll split this calculation into 3 panels. So let's say this is panel 1, which is the initial setup. This is panel 2, which is the extraction setup, panel 3. So this is after rotation of the factor loadings. So this is the last final solution after rotation. Okay, so I'll explain the interpretation or calculation in this, and in a similar fashion only the calculation is carried out in the later 2 panels also. So talking about this, since factor analysis is conducted on the correlation matrix, the variables are standardized. Okay, so each variable has a variance of 1. So you see each of these 16 variables which you have started with are having a variance of 1. Okay, and now if they have a variance of 1, that means the total variance, okay, so the total variance which can be there in this will be 16. So if 16 is the total variance, that means now I'm going to look at the so basically if total variance becomes 16, that's 16 times 1. Then the percentage of variance which gets explained by a particular factor can be found out using this calculation. So you divide the eigenvalue, say for the first factor or first component, the eigenvalue is 2.425. You divide it by 16, that is the total variance which it could have explained in the data, and multiply by 100, that will give you this. That is the percentage of variance explained. So 2.425 divided by 16 into 100 comes out to be 15.15%. So this is the percentage of total variance in the data formed by the variables, that is the 16 variables, which gets accounted by my first component or by my first factor. Okay. Likewise, you can always find out this value. So this will be 2.336 divided by 16 into 100, and so for third, fourth, and all the factors. Now, since I said that, eigenvalues are quality numbers, so we're going to take all those where eigenvalues is at least 1. So we see that for the first 4 components, my eigenvalue is greater than equal to 1. So these 4 components get extracted and I enter my panel 2. Okay, so here we see that the extracted components are 4, and you must always remember that the first factor will always account for the most variance. Okay, and hence it's going to have the highest eigenvalue also. Likewise, the second factor will account for uh, less variance as compared to the first factor, and so on. This number is going to decrease. Okay, so each successive factor will account for less and less variance. So we see that first accounts for 15%, second for 14, third for 12, and last for 9%. Okay, cumulative means it's just the sum. For the first entry there is no accumulation. Okay, it's 15, it's 15 only. For the second entry, for example, you see the number 29, that is a sum of 15.15 and 14.6. Likewise, third is a sum of all these three. Last is the sum of all of these. Okay, so that comes out to be a number 51.67. So we interpret this like this, that the first four factors in my analysis together account for 51.67 percentage of total variance. So that's how you look at the total variance explained. Now, as I promised that I would be taking up the interpretation in 3 panels. Now let's look at the second panel in particular. So what has happened here? So here you see that the number of rows are obviously equal to the number of factors which our analysis has retained. So our analysis has retained 4 factors, and hence I have just 4 rows here. Okay, the values in this panel are calculated in the same way as the values in the left panel, except that here the values are based on the common variance. Mind it, here the values are based on the common variance. So and not the total variance. So since the values are based on the common variance and not total variance, it would be likely that the values in this panel will always be less than the values in the left panel, because common variance is less than the total variance always. So for our case, I think this has come out to be same. Such a variation usually comes up when we use, the other methods of rotation. So we need not worry about that. But you can always remember that in extracted sum of square loadings, we can come up, or we could expect numbers which are lesser than on the left panel, because common variance is less than the total variance. Okay, now coming on to the rotation sum of squared loadings. These values represent the distribution of variance after the Varimax rotation. Since the Varimax rotation tries to maximize the variance of each factor, we see that the variation being spread over here. So you see that this percentage of variance column, the variation in the spread of this particular column is more evenly distributed as compared to the other panel. Okay, so we see that, here we had 15, 14, 12 and 9. Here we have 14, 13, 13 and 10. So that calls for a more even distribution. So this even distribution is possible because of the Varimax rotation. Because Varimax rotation set out with an objective to maximize the variance or the loadings on each of the factors. Okay, so this is so because the total variance now here gets redistributed over the 4 extracted factors, and we have an even distribution overall. So that was all about the total variance explained table, and it gave us an idea that, okay, in total, all of my factors are able to arrive or extract 51.675 percentage of total variation, and that we are able to extract 4 factors. Now coming on to the Scree plot. Scree plot also speaks actually the same story. So here on the x-axis you have the number of components or the number of factors. As I said, we are going to take each of the variables as a factors. So we have 16 numbers on the x-axis here. But out of these 16, we extract only a few, right? So on the basis of this table only, they have plotted eigenvalue, that is this total column over here. So in the Scree plot, we have these 2 columns being plotted, where this becomes your y-axis and this is your x-axis. And we know the story. So we know that we're going to extract the number of factors till the point where eigenvalue is at least 1. Okay, so we see that eigenvalue is 1 or greater than 1 till factor number 1, factor number 2, factor number 3, factor number 4. So only up until this point we have an eigenvalue which is greater than 1. So we're going to retain all of these components till factor number 4. Okay, and that was our solution from this table as well. So why is it called a Scree plot? Actually is this reason that, so basically this line is indicative of the percentage of variance being explained every time. So if you take a slope over here, so the steeper the slope, that means larger is the eigenvalue being dropped as you move from one factor solution to another factor solution. So that means there is a larger variance which gets explained at each successive step. Now that happens only until this point, because after this point we see a tapering off. So there is a tail-like structure here. This tail-like structure is also called as the scree. Okay, so we're going to retain the number of components till we get to a point where we get a scree-like curve. So this is a tail-like structure. So we see a tapering off of eigenvalues here. So from fifth factor onwards, we see that our line is almost flat. That means that each successive factors, you see factor 6, 7, 8 and so on, are adding too little in terms of the eigenvalue changes. Okay, so if you map the slope here, the change is not that remarkable. So they're accounting, so each successive factor is accounting for smaller and smaller amounts of total variance as the rate of change reduces. So that was about the Scree plot. Overall, the Scree plot as well as the total variance explained table allow us to come up that, okay, you're going to extract these many number of factors. Thank you for watching the video.